All right, we're looking again at graphs of polynomial functions. We looked at them before at what we can determine from the equation of the thing. This was expanded form. We're going to look now at what you can determine from when you have in that form. Now that you know how to factor, what we can figure out from the equation in factored form about the graph. All right, so to do that, we're going to, this particular function, these two forms, these are the same equation here, right? These are the same, this is the same polynomial expression, just one's in factored form, one's in the other form. We are going to look at a graph of those right now. Now there's those, both of them are punched in here, but just to convince you that the graph's the same either way, right? You get exactly the same graph when it's in one form or the other. So it doesn't matter which of those two forms. Now from this graph, we have looked at a lot of things that you could come up with from this expanded form. The fact that the y-intercept is 6 here, the fact that this is x cubed, so it has a couple turns in it. The end behavior starts down in quadrant 3 and ends up in quadrant 1. But we're going to focus down what you can find from the factored form. One of the things you can find is connected to these intercepts here. Okay, the y-intercept, as we said, you can see from this expanded form, it's the constant term. Now the reason for that, again, is because the y-intercept occurs when x is 0. And if you put x as 0, all of these terms become 0. If you substituted in x as being 0, all of these terms become 0, and you'd just be left with the 6. The same can be true from these, but it's easier to see what's going on when it's in factored form. This thing has x-intercepts at -2, 1, and 3. If you look at those factors, those correspond to the factors in this factored form here. X plus 2 is a factor because -2 gives you 0 when you substitute it in. You know that from the factor theorem, right? If you substitute in -2 and it gives you 0, then x plus 2 has to be a factor. Now extend that one step further. It has to be true that if -2, you sub it in and you get 0, well, that's the definition of an x-intercept, a value that gives you a y value of 0. You can see it pretty clearly when you sub it into the factored form. If I sub in -2 here, this entire bracket is going to be 0, which means this whole thing's going to be 0, which means I'm going to get a y value of 0. Any one of those three, you sub in, you get 0, which means they have to be x-intercepts. So something that we need to know here is the connection between these. The x-intercepts of the graph. X-intercepts of the graph are related to the roots of the equation, okay, or the zeros of the function. Okay, the zeros of the function. So if you know that you have a function that you can write in factored form, right? If you have it as x cubed plus, right, let's say plus 6 like the one we had there, you write it in factored form. Okay, why don't we just go up here where I actually have it written. Okay, you can take this and write it in factored form. That's going to tell you those x-intercepts. All right, the roots of these factors here, the roots of those, -2, 1, 3. The values that make each factor 0, the values that make the function 0, when you substitute them in, they're connected to the x-intercepts of the graph. So you need to know that connection. So let's go back to our graph for a second. Let's say I was to, let's get rid of these intercepts for a second here. Let's say I was to change this now and add another, like I'm going to change the function. So it's not going to be the same as this other one anymore. But let's say I added another factor here that was different. If I put x plus 1 in here, I'm going to put it in here because that's where it is going to end up when I graph this thing. All right, it's going to create, so I got to change my scale a little bit here. Move that up. So it changes obviously the graph into a 4th degree function now. We can't see them all here, but okay, there's my graph. It's got 4 x-intercepts, -2, -1, 1, and 3, correspond to those 4 factors there. 4 different factors crosses 4 times. All right. Now, I could have actually put in, if I had put in, say, x minus 1 again, instead of x plus 1 there. Let's see what happened there. Now, I get a 4th degree function, but it doesn't actually cross 4 times because I've put 2 of the same factor in here. All right? When you have 2 of the same factor, you're going to get different behavior around there. You're going to get this one crosses here at -2, but it just goes up and touches there at 1 because I have 2 of those factors, and then it crosses at 3. All right? So let's go back to here and look at it in a bit more organized way. When we're starting to have factors appearing more than once in a function, we're starting to talk about what's referred to as the multiplicity of zeros, how many times they occur. That factor that we had occurring twice means that 0 is going to have a multiplicity of 2. It's going to be what's called a double root. Now, to look at this, I want to look at, I have a graph set up here where we have 3 different functions, with the first one here that's showing right now has 3 different factors. All of them are different. And it has x-intercepts at -2, -1, and 1. Those are the x-intercepts. What we're going to do now is we're going to add an extra factor of x minus 1 and see what the difference is in the graph. So a shorthand for that obviously is putting squared there, or you could write it out twice the way I did before. Right? Write out that thing twice. Right now it crosses at each of those zeros. But if I change this now, leave the zeros on there. Now this actually crosses at the first 2, but then it just touches and turns around at that one. The one where you have 2 factors, it actually touches and turns around. We're going to think about why this happens here. Think about subbing in numbers on either side of this value here. We'll go back to the first one to do that. Think about subbing in numbers on either side of 1 into that first equation. If I sub in a number like 1.5 here, if I sub in 1.5, it's going to make that bracket a positive number. It's going to make that bracket a positive number, and it's going to make that bracket a positive number because it's bigger than 1. They're all positive. The values are positive on that side. If you go to the other side, though, let's say 0.5, these two will still be positive if you sub in a half, but this one will be negative now. So that's why it's below. One side it's above, the other side it's below. If I now change this to having 2 of those factors, or this number squared, number bigger than 1, they're all still positive. Right? We go to this, they're all still positive, so on the right side it's above. If I sub in a number like a half, x equals a half over here, even though that is a negative number, when I square it, it's a positive number. So it's going to be above there. It's positive on both sides of that. That's why that graph looks like that, and that's what you end up with when you have what's called a double root, the same factor twice, creating the same, having the same 0 occur twice. Now what happens when you multiply by x minus 1 even one more time here? So this is x minus 1 cubed on the end. This is going to be a 5th degree function, so we're obviously going to see some changes in the graph, but we're looking at the nature of what happens right there. Still going to have those same x-intercepts, but now it's got this kind of behavior. It starts below, and it doesn't just outright cross the thing. It levels out and then turns and goes up. That's called a triple root because 3 of those factors occur. Or you could say it's a root with a multiplicity of 3 because it happens 3 times. Just like you could say this one's a root with a multiplicity of 2. I prefer to just say double root or triple root, but that is up to you. Now I want to do one more thing before we leave this graph. When you zoom in on this, you zoom in on this point right here. Okay, zoom in on that. That looks like a, when you just look close on that, it looks just like a cubic function. Right? That looks like a cubic function. It's a triple root, something cubed. It looks like a cubic function at 1, right? X minus 1. If you zoom back out here, we can look at the whole graph again. If you zoom in on this one, it's a double root, something squared. If you zoom in on that, guess what it's going to look like? It's going to look like, sort of like a parabola, right? Not exactly, but looks a lot like a parabola. Turns around like that. That factor is degree 2, looks like a parabola. Let's go back out. I guess I don't need to zoom out every time, but kind of makes it better. Now, believe it or not, this one this only occurs once. If you zoom in on that, guess what it's going to look like? Okay, if you zoom in on that, guess what it looks like? It looks like a line crossing at 1 there. This is a degree 1, right? Single root looks like a line. Single root looks kind of like a line at that point. Double root looks like a parabola at that point. Triple root looks like a cubic at that point. All right, so that maybe is a way to keep it straight in your mind. And we'll go back to here. All right, so multiplicity. Multiplicity meaning occurring more than once. And it's connected to how many times that corresponding factor occurs in the factored form of the equation. Now, let's see if we can do something with this. Although before we do, I have written this out for you here. The terms double zero, triple zero, or double root, triple root. Okay, again, related to those factors. But now let's try something with this where we don't have the factored form and we don't have the graph, but we're going to try and predict something about the graph. How can we predict something about that? Well, you are good enough at factoring polynomial expressions by now that we can go through and factor this, and then that can tell us something about the graph. We can, of course, get what we know originally about these functions before factoring it from what we've looked at before. The fact that that has positive leading coefficient, and the fact that it's degree 4, and the fact that this is negative 10 on the end. We know a few things here. So we know that it's going to, it's a fourth degree function. It's its end behavior. End behavior is that it's got to start up in quadrant 2 because it's positive. So it's got to start there and end there. It's got to start up in quadrant 2, end up in quadrant 1. Starts up in quadrant 2, and it's got to end up in quadrant 1. That's got to be its end behavior. It's got to have a y-intercept of negative 10. Y-intercept of negative 10. You could say, you can say 0, negative 10 if you want, or you can just say negative 10 like that. And we know it has a maximum of 3 turns. 1, 2, 3. Now it might not. It might have only kind of like that or something like that, but it can have up to 3 turns like that. Now we got to know what we're going to look for after this is we're going to look for those x-intercepts. To find those x-intercepts, we got to factor that. So we're going to get this stuff out of the way for now. And I'm actually going to keep this for later. So what we're going to do is shrink it down and leave it over there. But we want to get this down to a factored form. This might have up to 4 factors. It might not, because it might be that, you know, it can have up to 4 x-intercepts here. It could cross once, twice, 3, 4 times. But it doesn't have to. It might cross once, twice, and then just turn around like that. It actually doesn't even have to have any x-intercepts. An even degree function doesn't have to have any. It could look like that. But that would have been pretty silly of me to create a polynomial function that doesn't have any x-intercepts when the point of this whole video is to make connections between x-intercepts and factors. So chances are pretty good it's going to factor. Now, since you're already such experts at factoring, and I don't necessarily want to, this is going to take a little while because 4th degree, you got to go at it a few times here. I don't want to take tons of your time up, so I'm going to do this at supersonic speed. Are you ready for me to factor this at supersonic speed? Here we go.
First I'm going to try x minus 1 as a factor. I'm going to sub in 1. 1 to the 4th minus 7 times 1, except when I do that in my head. 1 to the 4th, 7 times 1 to the 3rd, 9 times 1 squared, 7 times 1 minus 10. last time here. X minus 5, x minus 2. Keep the other ones here.
That's the factored form of that function, and that's going to tell us our x-intercepts. X-intercepts are 1, -1, 5, 2. Right? Those are our x-intercepts. And we're going to try and draw a graph of this. First, we're going to go back and get that other information that we had before this. Bring it down because we're going to use both those pieces of information together to create a really rough sketch of the graph. And then check if we're right by using some graphing software. So we need a, not that we're going to use the grid really all that much, but we'll do that. We need some axes here that we can use. So we'll use those axes there. We'll just use a horizontal scale of 1 square is 1, and maybe vertically. Since we got our y-intercept of 10, we'll say that each square is 5 this way, so that's going to be 20, and this is going to be -20 down here. So we're trying to graph these things. We have y-intercepts of, or we have x-intercepts of -1, 1, 2, and 5. And we got a y-intercept of -10. Now we know it more or less has to go like that. So we have to, it has to pass through, it has to start up here in quadrant 2, it has to end up here in quadrant 1, and it has to pass through all of those and that. Now the only sort of general shape we can draw then is this. Maybe it turns around somewhere there, it doesn't go much above. Now it probably goes more down below there, and something like that. Now that's a really rough guess. It's hard to know how far down it goes. It may well go down a bit further or not quite so far. If we really want to get these points, that's later on when you take calculus. You can find those nice and easy algebraically. But that's our general shape of the graph. Now we're going to look and check here. So we'll graph this using some software and see what it looks like right now, and see if we're right. Now I have it actually just going to paste it here. There's that graph. Now it has what we thought, right? X-intercepts at -1, 1, 2, 5. Lower down here. Now this is lower than we had it as. We had it crossing here. I actually had it drawn so that it had a, you know, it had its minimum at the intercept there, but that's probably, I mean, this is obviously more accurate. The minimum is a little bit beside it there. It's on its way up, a little bit above, but the general shape's about right, right? We have the x-intercepts right, the y-intercept right, right? Now, one last thing we're going to look at here is if we're given the graph and we're going to try and figure out the equation of this. All right, so kind of working backwards here. Now, hopefully at this point we're good with making the connections here. From that graph you can tell it's got x-intercepts those 3 places. So it's got x-intercepts at -3, -1, and 2. And this one, the important thing to know is that is where the graph just comes up and touches. That's a double root. So let's write that down here. This one is a double zero or double root. Now the other information we can get quickly is there's a y-intercept there of -60. Y-intercept of -60. Right, we know that maybe some other things to notice are the end behavior of the thing. It goes down both directions. All right, so the leading coefficient has to be negative. Lead coefficient is negative. So those are just some things that we can use to make sure we've got the equation right once we try and write something here. The place to start is with those x-intercepts. Try and write something to do with those factors, right? Because that's the critical part, and then we can look at the other stuff here. If we write an equation that has that, it does say it's a 4th degree polynomial. If I have -3 as a 0, x plus 3 has to be a factor. -1 means x plus 1 has to be a factor. And that double 0 there means I need two of these here, x minus 2. I'm going to write it this way for now, but you could write the shorthand, of course. So, is this our function we're looking at? It certainly has all of these, but you got to think about, does it have the other things? Does it have a y-intercept of negative 60? Who knows? Let's see. What if we, what if we multiplied all this out? If we multiplied all this out, it would start with x to the 4th. You'd have a bunch of terms, and the last term would be, think about what it would be. The last term would be 3, 1, all of this stuff multiplied. It would actually be plus 12. That's not what we want, right? Because two things there. The leading coefficient's positive for that, which would mean the end behavior is up, and it would cross there, there, and it would have a y-intercept about here somewhere, right across like that, have a double root and look like this. So that's definitely wrong. It meets part of the criteria, but not all the other criteria. But the little trick here is that you can change this graph without changing the intercepts. There's a certain kind of transformation you can apply here to a graph that doesn't change any points. All the points along that axis don't change. There's two of them. There's a vertical reflection and a vertical expansion or compression. Now the way you can do that here is by multiplying this by a number here. If I put a number 2 in there, all it's going to do is double all of these. It's not going to change any of the intercepts. Those are still going to be factors, but all of these coefficients are going to be twice as big. That means the y-intercept is going to be plus 24 instead. This is going to be a 2 here. Or I could actually multiply it by a negative, right? If I multiplied this by a negative 2, I would change that now to negative 2x to the 4th. This would be negative 24. So that's starting to look a little bit more right here, because this is what I want. I want a negative leading coefficient. If you think about what you need here, the way it is now, I have that. I want two things. I want this coefficient to be negative, and I want this last term to be minus 60. I need it to be minus 60, so you can think, what value do I need to put in here? I'm just going to call it k, a value that I'm going to multiply by there. What value do I need to multiply this whole thing by to get those values that I want? If I have positive 12, but I want negative 60, I think you can see probably that you need to multiply this by negative 5. If I multiply that by negative 5, I get negative 5x to the 4th at the beginning, a bunch of terms in the middle, and negative 60 on the end. There's that way of looking at this, just kind of comparing and thinking about it, or you could actually write an equation and sub in a value to find it, right? So if let's say I wasn't sure what I was looking for there, like this. Let's say I recognized that I needed to put a value in front, but I wasn't sure what it is. The way I can do it here is sub in this point, use this point here, saying that when I put in 0 into x, I need this to be negative 60, and then you can just work out the rest of it here. So 0 plus 3, 0 plus 1, 0 minus 2, 0 minus 2. Now, 3 times 1 times negative 2 times negative 2, that has to be negative 60. Or in other words, k times 12 has to be negative 60. You can divide it. K is negative 60 over 12, which is negative 5, that number that we have there. So you can actually work it out by writing an equation with a variable in it and solving, or you can just do it intuitively by comparing the intercepts here of the function you came up with and the one that you need. Now before we're done here, I just want to show you graphically what's going on there. So this is the graph of that function that you need. That's the original function that we came up with here, right? No value in front there. So it looks quite a bit different, right? But if you do that same thing, but you put a k value in front, now right now this k value is 1. If I change that, if I increase it here, it expands that vertically. Now let's make this a bit thicker here first. There we go. And if you change this the other way here, if you make it a negative number, it does that reflection, right? Now we want it to reflect and be enough that that it matches up with that y-intercept, right? Whoa, what's happening here? There we go. On this side, if you start to approach -5, you notice it's going to match up there. That's that vertical reflection and a vertical expansion. All right, if I had stopped at +5, it would be exactly the opposite of what we wanted there, right? Vertical reflection, which tells you need that -5. All right, so that k value in front there, you can put a k value. Doesn't notice again, it's not changing the intercepts, the x-intercepts. It's changing all the y values, expanding or compressing there. So that's kind of using your knowledge of transformations to solve a problem there. All right, that is more or less it. Even though that's a tough problem there, it's involving the concepts that is involved here that we're looking at today, which is how those factors are connected to those x-intercepts there. All right, that's the main idea here, is knowing that connection between x-intercepts of the graph and the roots of that equation, or the zeros of the function. The zeros of the function, the x-intercepts of the graph, the roots of the equation. So that's it. If you can make that connection and use it to solve some problems.